Geometry tells us what shapes are. Differential geometry tells us how they live, move and flow. It is not just about lines and curves on a page, it is about understanding the bending of space, the turning of a path, the way motion and shape interact. In this journey, we won't just look at curves, we will feel how they move, twist and respond to the world around them. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to the second video in learning the essentials of differential geometry. First, let us look at a quick recap for those who have missed this earlier lesson, or I have put it in the I button also, you can go ahead and check. In the first lesson, we learned a little bit about what is differential geometry. I'm going to say what the idea is and how they interact with different smooth shapes and spaces. We also looked in what is an implicit equation, what is an explicit equation. Obviously, differential and geometry, these are the two words which uses both calculus and geometry. We understood what is implicit equation, how they look like, what is the importance, what is the definition of a curve, and from R2, if we move into the three-dimensional space, how they look like. Now, this first lesson was basically on a brief introduction about differential geometry, and we would start today's lesson in understanding more deeply what is a curve. Now, in general, when we look about curve, we generally mean something, a very difficult mathematical notation, but we won't look at that first. What we are going to look is that we are going to look into what is called a basic layman's definition of what is a curve. Now, in our daily language, we mean curve is something which is a kind of a wiggling shapes like these blue lines which comes over here and there, etc. So this is in general, whenever we close our eyes, or a general notion of what is a curve. So in our everyday language, when we talk about curve, these are basically bends or loops or something kind of a winding road or a loop. But what I would like to imagine you first is that imagine you're drawing on a paper without lifting a pen, and what you draw, it can be a curve, it can be a straight line or bendy like a spiral, but what matters here is this one. It is called the flow of continuity from one point to another point. So what we can say is that a straight line is a curve without zero bending, a circle is a curve with constant bending, and a helix or a spiral is a curve with changing bending and twisting in space. So in the general sense, what we can say is that a curve is a smooth path that a point can follow without jumping or lifting your pen. So the word curve in math is more generic than in everyday speech. It includes all the possibilities, not just that bends, because in general we see that whenever we talk of curve, we generally mean bending, but it is not so. What matters is that it is continuous and it follows from point to point. Now, when I take this kind of a definition or a notion that what matters is that it flows continuously from one point to another point, this requires a little bit of introspection. First is that if you zoom in or any two very close moments here in a time. So here is a line and you're zooming it at very close moments in time. The dots or positions are also very close in space. So what do I mean by that is that every point in the straight line, if you zoom it further, it connects to its neighbors. Also, you will see a smooth curve does not suddenly change direction or speed in a single instant. So here is the smooth curve. You can see that it doesn't necessarily change direction and speed in a single instant. So even the twists and turns it takes, it happens through time and it takes many tiny turns. The second thing is that what I would like to tell is that it is a steady motion. Remember, a smooth curve, and it doesn't happen very abruptly. Now, if I take a kind of a curve like this, we label the position along the curve with the parameters called t. Now, what is parameter? Why we are defining? We will come to those part later. So let us imagine this to be a curve, and what we are doing is that we are mentioning with the parameter t. And here you can see as t increases. So here is t, here is t, here is t. So as t increases by a tiny amount, the curves also moves a little bit. So what I would like to tell you is that for every little tick from t to t to t, so for every little pick of t, you get one new point in space on the curve where there is no skipping. So why it matters? Now you might say that all these things, why does it matter? It matters because movement is continuous and you can talk about velocities, direction, speed and curvature and how sharply it bends at each point. So your pen never lifts over the paper, the ink flows in an unbroken line. So this is another notion of what we call is a curve. So obviously from here there is a question which will be coming into your mind is the definition. So we can say on a very layman's language again that a curve is a smooth path that a point can follow without jumping or lifting the pen. Now there is again a question which would come is that is straight line a kind of a curve, because we do not see any wiggling or bending. So is straight line also curved? We can say yes, in differential geometry it is, because any continuous smooth path including straight lines is considered to be a curve. So remember that what is the key idea? The key idea is here is basically smooth and continuous. So a straight line is just the simplest type of a curve, but it has got zero curvature. So key idea is smooth and continuous movement. So any continuous smooth path, including straight lines, is considered to be a curve. Now here is a few important points which would eventually emerge is that in mathematics, curve actually doesn't mean something has to be bending or wiggly. A straight line is just the simplest kind of a curve. So in the world of curve, we can say straight line is just a special, but it is an unbending curve. So a circle is a curve with a constant bending, straight line has got zero bending, and a wavy or wiggly path is a curve with certain kind of a changing curvature. So this is some kind of a notion and understanding, a visual depiction of what is a curve. It is not that it has always to be a straight line. Now, what is the simplest equation of a curve? This is what is called the simplest equation of a curve. And here you can see that A, B, C, D are constants I have given. It is in T is in R, so obviously it is including the real numbers. So if I plot this, we get this kind of a graph. So what I would say is that here both X and Y are changing linearly with T. Right? Both X and Y. And as T increases, the point moves in a straight line. Obviously, it has got no bending. This red line, the red arrow shows that it is a straight line with no bending. Now, if I take this kind of a notion, gamma T equals to T, comma 2T, it actually, if you plot it, it gives a kind of a straight line. So what does this mean? This means x of t equals to t, and obviously a y of t or gamma of t would be equal to 2t. So if I now get this kind of a graph while we are plotting those areas, so what we get from here, what you can see is that when t is -1, the pointer -1 and t. When t is 0, you can get 0, 0, 1, you get 1, 2, and 2, you get 2, 4. This is pretty simple. I mean to say how you are actually drawing the curve, etc. So from here, when we turn the page, what we get is that the generic equation, in general, the equation is written as this for R2, and in generic equation for R3 is given by this. So this is a very kind of a generic notion where all these t, this is called the parametric equation, and all these t, which is pointed in these maroon lines, this is nothing but a parameter. Parameter, just like time is a parameter. And all this x of t, y, t, z, t are basically coordinate function, and they tell actually where you are at that particular time. Now, if I consider gamma t, this is the position vector at time t. That means it actually describes where the point is moving. Next, we go to this t. We know that this is basically the parameter. For simplicity, let us understand it is time, and it controls where you are along the curve. These functions xt, yt and zt, these are the coordinates at a point at the time, and the collections of all points gamma t is actually the path which is traced out in space, which is what you see. It can be a straight line, a circle or a parabola depending upon the equation. So this is a generic equation of a curve which we understood in 2-dimension and 3-dimension. These are the different notations, and what do the notations mean? Now we next come to a very important part which most of the books and the learning actually doesn't mention. It is called a way of defining curve. What are the two ways of defining a curve? Coming up next in our video. Now here you can see that in general a curve is defined in two ways. First is called an implicit definition and second is called an explicit definition, or we can say parameterization. Now both of these way of defining a curve is equally important. Equally important in the sense, I would say, each of them has got its own meaning, and most importantly you will see that each of these meaning has got a limitation also. First, what we will understand is that what is an implicit definition of a curve. So in general, a curve in mathematics is defined in two ways, which we have seen. The first is what is called an implicit definition. Implicitly, we define a curve as a set of points which has got a scalar function. As you can see, C is basically a constant. So from here, what we get is what is called a level curve or a contour line. I will come to this meaning what is a level curve. But a level curve, what is a level curve? A level curve is basically the set of points, for example, x, y in a plane where a function f of x, y has the constant value. What does that mean? Say, for example, this is a person who is walking, and you can see if he is continuously walking, the level curve tells that the height is the same. So just imagine it is you are walking around a path, around a park or something, but the height is always the same. This line, this black arrow, it shows that the height is not changing. So that means you're neither going uphill, neither you're going downhill, and you're walking constantly. Now, as it is technically called, this is also called a contour line. That is the level from, it is the height from the sea level. This is basically what is called the contour line. So you walk and walk, but what is happening is that your height is not changing. This is basically what is called the implicit definition of a curve. Now, let us see that how does it mean. This is an analogy, the contour lines, the person walking. But in mathematical definition, as you will see over here, is that let us say we take this kind of an equation. As you can understand, this is a circle. Then the level curve f of x, y equals to 1. That means that the circle has got a radius 1 and all the points are exactly what we call 1 unit from the origin. And this gives up what is called a unit circle. I'm not going to explain over here what is a unit circle because you understand everything. Now, taking this definition, if I plot mathematically, the level curves would look something like this. The red dot is basically what is called the center, and then we have got the circle or the concentric circles going around here. So the value of the function, what we have seen over here, is that the level curves would be f of x equal to x squared plus y squared is a constant. Now, if it is a constant, then this is basically what is called the defining property of a level curve. So a level curve, how it would be, the defining property and the most important property is it has to be a constant. So for example, in this left hand side diagram, if I take the innermost circle, it would be 0.5, then it would be 1, and then it would be 2, and so on and so forth. So what is changing? The value of f of x, y. What is constant? That is the value, and what is changing is your position along the curve. So each blue circle can actually represent a path at a fixed altitude. So you can, for example, understand that altitude is say 500 meters, 600 meters, and so on. So the value of f of x, y is increasing, and as you are moving further and further from the origin, what is happening that x squared plus y squared is increasing. So the radial distance here, f of x, y, increases. Now let me give you another analogy of this. Now let us, for example, imagine this kind of an animation. So here what is happening that as you walk around a circle, your altitude never changes. It stays the same. So you're not going up and down. F of x, y is fixed and you're staying on the same height or level. And the level curve actually tells where you are, but it never tells how you're moving because it is all constant. So this is what is called a level curve, which is defined implicitly, and it actually helps to visualize how a function particularly behaves. So you go around and around, the height is not changing. Now, if I now take a kind of a level curve with a parameterized curve, which I will coming to that later, here you can see that here, this one, the red curve shows the parameterized circle. And this parameterized circle actually traces the level curve where it is equals to 1. And the blue contour lines that you see, the circles, have fixed values, and the red circle actually gives us a way to move along one of those level curves using a parameter t. But let us not get confused with what is a level curve versus a parameterized line, but this is just to give an idea. So whenever we are defining a level curve, we understand it is equals to c. That means it is basically a constant. So what do we get from here in implicitly defining? So what we get is basically a set of points from the curve, that what we are getting, and the shape or geometry of the curve in space. But as I told you that every definition has got its limitation, level curve or implicit definition also has got its limitation. What are the limitations? First of all, we don't know how to move along the curve, in what direction. We also don't know how fast we are moving, the velocity, and how that movement is changing. That means the acceleration. And the reason is that you might ask me why? Why? Because level curves don't provide a parameter like a time t, which can help you to trace the curve, right? So there is no information, absolutely no information about where you are on the curve at a specific given time or a moment, which way, the direction that you're moving, and whether you're speeding up or slowing down. Nothing actually is being known. So these are basically what is called the problems, I would say, what are called the limitations of a level curve or implicit definition. And in order to save and help us to know more mathematically, what we use is called a parameterization. Now, if you go to my earlier video, that is lesson 1, this is the thumbnail, you will see that I have spoken a lot about level curve in the first lesson. So how the level curve f of xy is used in parabola, straight line, circle, etc. So we are going a little bit more ahead in this definition. However, this is the limitation which I have not spoken in the first video, but which I am doing in the second video. So as I told you that in order to overcome that limitation, we need what is called a parameterization, or in another way we can say that it is an explicit way of defining a curve. Now, what is a parameterization? I don't want to go in the mathematical part immediately, but I would like to explain you in this way. It is a way of describing a curve by a given coordinates which has got a parameter, a variable which has got a value which is called t. Now, I want you to imagine a train which is running along a track, right? The track is like the curves. Now, the parameterization is like a train schedule. For example, at time t0, when the train is starting at a point x0, y0, as we move ahead from time t0 to t1, the train moves at a new position x1, y1, and at time t2, it is somewhere at x2, y2. So the curve is traced as the time follows. So here we can say that parameterization is a kind of a schedule that tells that what time at the train is at what position. So what it tells is that it tells you the track, the shape is the geometry. You can imagine the rail track to be a geometry, and the schedule tells how fast the train moves, where it is, and in which direction it is going. So with a parameterization, what you can understand is that the speed, which is called the first derivative, the bending, the second derivative, the total distance, and the change of direction of a curvature. And what happens if you don't understand parameterization? So without a parameterization, you can only have the track drawn, that is the implicit definition, and you don't know how the train moves on it. So this is something which I would like you to imagine. So with parameterization, you can study the speed, the bending, the total distance, and change in direction. So in one word, we can say that parameterization is just like the train schedule. It tells you where the track is. It tells you not only where the track is, but where the train is at every moment. It brings the curve back to life. Now, this is a kind of a layman's definition which will make you easy understand. Now, in case of a mathematical definition, for example, if we take this kind of a situation where we are doing a circle which has got of a radius, for example, 3, centered at the origin, then we got the parameterization, which is this one. Gamma t equals to 3 cos t, 3 sin t. Again, t is the parameters. And here, xt equals to cos t and sin t. So this is what it means. So it means that whenever I am at a t equal to 0, that is 1 comma 0, it shows this one, which is the rightmost position. When t equals to pi upon 2, 0 comma 1, I am at this position, which is the topmost position. And t equals to pi, I am getting at this position, which is the leftmost position. So what it tells is that this particular graph, as you can see here, you can clearly see that the green arrows showing the direction of motion as the t increases, the green arrows, and the point moves continuously, I would say counterclockwise around the circle. So this is what it does. So in a strict definition of parameterization, we can say what is parameterization? In R2 it is known as this, and in R3 it is known as this. So as t changes, we get different points x, y or x, y, z. So why do we need parameterization? Because a curve is not just a collection of points. It is a kind of a path where you're steering along, where you're going along. So the parameterization actually tells you the story, where it starts, where it goes, and how fast it moves. And it is important to know all this in learning differential geometry. So we move on the next part of our video, where we will demonstrate to you that how to use parameterization to define curves. Now, in order to do that, I would like you to imagine a parabola. For example, gamma t equal to t comma t square, where t is in. I will explain all this part. So what this means is that t is like a parameter, you know, which is a time. Now, at each point of t, you get different values. So when t is this one, you can see this minus 2 comma 2 within braces. This is what is called a restricted interval. That means it has got a certain interval which is very restricted. Here it is. It is 2 and minus 2. So it means that actually the parameter t is only allowed to take specific values. If it is not allowed to take specific values, it would have run from minus infinity to plus infinity. So in order to restrict that, because infinities are something mathematicians really don't like, but it is a restricted interval. That means it has got a certain boundary. Now, the question is that what is t is doing here? So here you can see when t equals to minus t, the point is at t comma minus 2 power 4. Here you can see it is minus 2 x axis, and this one is 4. When t is 0, it is at 0.00, and when t is at 2, the point is at 2 comma 4. So the curve is basically given by this particular notation, gamma t equals to t comma t square, meaning that xt equals to t and yt equals to t square. So here you can see that the blue curve is the path traced by this, and the red point marks specific values. So as t moves smoothly from minus 2 to 2, the point flows along the parabola. And this is how exactly how the equation actually looks like, and the curve actually how it looks like. So here you can again see that what t is doing over here. What is the function of the t? So t is the parameter. You can think of it as a time. As you change the position, it also changes, and the curve is the path as it is traced. So here you can see, if I take this kind of a a table where the different values of t, xt, etc. are pointed over here. Here you can see that at basically t equals to minus 2, you are at minus 2.4. At t equals to minus 1, you are at minus 1.1. At t equals to 0, you are at 0.0. At t equals to 1, you are at 1.1. And t equals to 2, you are at 2.4. But all these are nice and fine. But here comes a very intuitive question in your mind, in our mind, that why do the parabola takes this kind of a U shape, or why the parabola actually bends? This is something which I would like to explain to you, a very important concept, why the parabola bends. Now, I would take the same graph, obviously. The bending here, remember, happens because the x-coordinate grows linearly. As you can see, the x is growing linearly, straight, but the y-coordinate grows quadratically. That means what is called t-square. So linear growth moves at a steady rate. Quadratic growth moves faster and faster as t increases. This mismatch between x and y creates a bending of the curve. Now here you can see the same graph I have pointed out. Now you can see here that when t increases from 1 to 2, you can see that when t increases from 1 to 2, x increases by just 1. You can see it from the graph and from the table itself. But as y increases by 3, So t increases from 1 to 2, x increases to 1, and y is increased by 3. So y grows faster than x. So the curve moves upward, more upward than horizontally, and this is why the curves bend upwards. This is a kind of an understanding of why the parabola bends. So from here, when we move to the next part, we can use all the graphs together. And here you can see that there is no bending. This is gently bending. And now they have seen that x grows linearly and y grows quadratically. And this is a kind of a constant bending. So then we come what we call, if you go to any book of differential geometry, what is the formal definition of a curve, which sometimes comes a little bit of confusion. So the formal definition of a curve is essentially a smooth continuous path traced by a point moving through space. And this is given by this. I would like to give you an understanding of what this equation is all about. Here this is called a function or mapping. The gamma, I is an interval. For example, I would say, you can say gamma is a kind of a machine or a recipe. I is an interval for a timeline. For example, it goes from 0, 1, 2, 3, 4, 5. And this is nothing but space in 2 dimension, like 2D x and y, in 3 dimension, x, y, and z, and so on. So it can be Rn. So what it says is actually, if you input a kind of a value, it actually says if you input a value from t, from the timeline I in the machine gamma, and it outputs, gives a point of a space, either 2D or 3D. Now imagine a ride that moves through for example, a beautiful park. Here you're sitting with your family in a beautiful park, and you sit on the riding car. And here you can see that this t is basically the time. That means how long you have been riding on that park. Gamma t tells you actually your position at time t, where you are inside the park. And as you know that t changes, you move along that beautiful path which is through the park, and it can be 2 dimension or 3 dimension. That is why it is either R2 or R3. So this is a kind of a formal definition and the notation. Now here you can see one thing, that in the earlier this definition, there is nothing which is called a t. But here we are talking about t, and t. So where is this t from this definition? This is something which is very important. Now here you can see here that t is actually not written. Why? Because I is an interval. It means it is some kind of a number from a real line. So when we actually use the function gamma, we have to pick a variable. That means instead of using the function, there has to be a variable which has to be done, which represents the interval, say for example 0, 1, 2, 3, 4 and 5. So that is why we choose a letter to represent a value inside I, and this variable is called t. So remember, t is nothing very special. It can be anything. It can be s, it can be tau, it can be p, anything. So suppose we take this kind of an interval, the numbers, for example, like times 0 to 6.28, and here also, so the t is just a representative point from the interval I, and when we plot t, what we get is the value of the space, that is Rn. Right, so it is basically, it is not the part of the definition. It appears when we work with parameterization. Right? So t is just a representative. When actually using gamma, we just select the letter for the input value, and we actually get a kind of a t. So this is what is the formal definition of a curve, how it looks like, and what are the meaning of those equations. Now, this parameterization actually leads to a lot of important consequences. For example, it would lead to a velocity vector, which means is the first derivative which points a tangent to the curve at each point. We get a tangent line, which is important to study. We get speed. It tells you how you're moving or stopping at some points. You also calculate what is called the arc length, which is how long the road it is, very important and practical. You also need to know what is a curvature. That means how sharply you're bending. You need tangent vector because here the direction or the length is 1, and a normal and binormal vector, which is actually coming from what is called the Frenet-Serret frame. Now we will learn all these consequences of parameterization. These concepts like velocity vector, speed are something related to physics. So is this related to physics or some kind of an abstract thinking? All this we will learn in the subsequent and the consequent videos which are coming up. So that's all for today's video. Thank you very much for watching this video. If you like the video, please hit on the subscribe button to subscribe to my channel Physics for Students, and you can click on the bell icon so that you get all the notification from Physics for Students. You can also subscribe to my other channel which is exclusive to Einstein's General Theory of Relativity, and you can contact me where I generally try to respond as early as possible. Stay tuned in the month of May because there are very important and interesting podcasts which are coming up, and with a series of lot of other videos in differential geometry and other subjects. Thank you very much for watching. I will wait for your comments and see you soon in the next video. But till then, may the good Lord be with you.